Great. So coming up now is Herbert Poetzl and Sebastian Pichelhofer. They've been working for the last half a year on full-time on an open source digital camera, professional version, and they're about to launch the beta. They call it Apertus AXIOM. So you're talking first. Great.
Thank you. Okay, good morning. Many thanks for being here. Let me start, because the idea of the project is sometimes a little bit difficult to explain in layman terms. So one quote I always love starting the talk with is a quote from an IMAX cinematographer from a couple of years ago. And to him, he says, "I grew up as a photographer in the dark room and missed the intimacy of watching the images slowly appear in the paper in the red of the safe light. The beauty of an open source camera to me is a step back towards the darkroom in which making the tools is part of the joy of making the art." That sums up all the reasons why we are doing this and why we are here. And let me start by explaining a little bit about the history of the project, or the history that led to the project. What you see on screen right now are 50 years of digital cinema camera development. This is from the 1950s, basically, and on the right is the Sony F65 from a couple of years ago. And what happened in these years? Actually, we would think that the technical developments and the advancement in cinema projection and all that has made leaps of progress in the time. But what actually happened, while with no doubt the image viewing experience and image quality has improved, is that the freedom and the control the DOP or the user of the camera has actually decreased in recent years. And so while you had a mechanical camera that you could manipulate, it had motors, it had just the essential parts of electronics that they had at the time, you could all change that, you could all understand that, you could change how the light hits the film frame, how it is exposed. And on the right, you have a camera that's basically a black box that you have no control over. You have a few buttons that you can press, but nobody knows what's really happening inside these devices. And that makes us, or you, the camera users, basically a puppet in the hands of the camera manufacturers. And that creates or leaves you with a black box with a lens on it. And that's exactly where we come in. And maybe you have wondered what this strange Apertus name actually means. It's a word from Latin, and the Blendenöffnung, the aperture, actually comes from the same tree of words, and that just means open, frank, free, clear. And where are we from? That's for the history section for now. We are in the international team from mostly Europe, but we also have team members in Australia, South America, America. Even a guy from India recently is helping us a lot. And it all started a couple of years ago with a company in the United States that got big by building universal system scientific cameras that were used, for example, in Google Street View. And they built the first actual open hardware and free software camera, but it wasn't perfect for filmmaking. The project started with kind of modifying and building the stuff around these cameras to turn it into a device that could be used for film production, but it has a small sensor format, for example, which isn't optimal for film production. It had other few drawbacks. So at some point, we decided that it is time for us to build our own camera from scratch. We started with some design studies and illustrations and made plans and drawings how this camera could look like. We came up with an open module concept, as we call it, where you can stack different kind of hardware modules after each other and that way expand or utilize the modularity of just swapping parts that are outdated or that you want to replace. And we came up with a number of modules that could make sense in that regard. Like you can have a storage module or a raw recording module or dedicated modules for audio and all kinds of different things that we haven't even come up with so far. So we also created a template design module, which is kind of a blank Arduino shield, if you call it that way, where you can just add your own hardware and software for doing the things you want to have in the camera and have it natively integrate into the camera hardware itself that way. It's not a kind of peripheral, but it's actually a part of the camera itself. It has the interface to all the internal camera data that you have from any other point in the camera production pipeline. And we call this the open modules concept. It's just an illustration and a little bit of text. We extended this open modules concept then to the front, because everything you have seen so far regards just to what is after the actual camera block, like the modules for processing. But you can also change the modules in front of the camera now with this second iteration, which means you can have a modular lens mount, a modular filter mount. You can change the lens base independent of the lens mount itself. And that way you can also swap the image sensor module, which is an essential part of every camera and every digital cinema camera, like you had film stocks in old analog cameras. The plan is now that you can also swap the image sensor like it was film stock in the camera. And what we have now, what you have seen so far is like the dream that we are chasing. What we have as a first step now is a camera prototype that we call the Axiom Alpha. It looks rather fancy when it's rigged in such a big rig with viewfinder and recorder and mat box and shoulder grip and everything. What you can see outside is the bare bone version of that camera, which is basically just a black shoebox with a lens attached. And it already uses most of the hardware or the electronic components that we want to have in the final camera, but a simplified way of implementing the essential features that we need to just get to a point where we have actual live video coming out from the camera that we can analyze the image sensor and look how the image is actually kind of perceived and how the look of the sensor is and what the camera could make up for an actual production where you shoot film then.
Okay.
Yeah, there we go.
So basically we wanted at the first step to show that this fancy project you've seen in the illustrations can actually be done by developers, free software and free hardware developers, and that we actually can make a camera which has 4K resolution and an acceptable frame rate work. And this was the reason for the Axiom Alpha prototype, which is based on the Z board, which is an FPGA development board. And we added a sensor front end, which we designed ourselves to connect an available and well-documented sensor with the necessary features to our development board. And then we basically started hacking on it to get it to a point where it's actually usable. Do we have
the hardware components? Yes, we will skip the live demo that we actually plan to have and do that outside where we have the prototype right now.
So I guess most of you already saw the Axiom Alpha outside and the image on the big screen. Here is how we basically started. You see the sensor board on the right side, which features the sensor on a socket and some other components to supply the sensor with the required voltages and do some kind of monitoring. We also have 2 temperature monitors below the sensor. And it was basically built to be kind of flexible. at this stage. So we had a number of regulators we didn't even populate in this version, and the jumpers basically would be able to disconnect power lines from the development board to the sensor board, so that we are very flexible in trying out different things and getting the thing to work, because we had no idea if we could do it and if the power supply and other stuff would be sufficient. On the left side, you see the set board with two debug modules attached, the sensor front end and the sensor, as well as the lens mount. This is the original aluminum version we had. And the connection, the special connection to actually trigger the sensor is the big black wires, the two black wires here. Okay.
Next slide is about the
Yeah.
debug modules.
This is, in my opinion, a very good example how open source and open hardware development can be very beneficial if done properly. Because we had, or I had the requirement to get some kind of debug information out of the set board, and the set board has 8 LEDs, so the amount of information you can output there is quite limited. And I started first with using those 8 LEDs, and the next step I tried to bank them with the switches, so you could basically select 8 out of 32 or 8 out of 64. And still this was quite complicated and not really easy to handle. So I thought to myself, I design a board which has a number of LEDs on it and plugs into one of the interfaces on the set board and can be controlled with a few lines of VHDL code. So this was created, and we ordered those on Oshbach and built two, actually quite a number of them. And we had our debug environment, which was readily available and visually usable, which basically makes the human brain, the processing unit, the debugging, the debugger. And it worked quite well. We actually debugged a number of things with those modules. For example, the interface, the bus interface, which is on this board a somewhat proprietary version of an open design, and we had several problems to figure out there, and usually the system locks up and you have no idea what happened. And in this case, you could simply look at the LEDs and tell what the current state is. And we came up with a number of other modules over the time, which one special fun development was done on April the 1st. We made an April Fool's joke where we claimed that a gaming company is interested or is buying us to create the next version of gaming console. And for this purpose, we simply designed a simple controller. The case is completely laser cut, nothing glued, only assembled. We designed a small PCB which basically consists of a regulator and a digitizer which creates I2C data from the position, which is a kind of small pedal device, and we implemented Pong, the game, on the camera. So one part, small C code, which has the gaming logic, and another part in the FPGA which does the overlay and creates the illusion of a working Pong game. And we actually played it for quite some time. There are videos online from this time. I think it was more than 1.5 hours where we played, because it's a funny thing to do if you put the camera in such a position that you're on the screen, and the overlay is also on the screen, so you basically see the reaction you have to certain situations.
Actually, it was just kind of the silliest idea we could come up with, how we could implement Pong on a cinema camera. But while playing it, we actually discovered that the game itself is actually lots of fun, because you can see your opponent when he misses a ball on screen already. It's incredible. So maybe we can actually sell the camera as gaming console at some point in the future.
So, but mostly this was, in my opinion, a really good example how you can extend such a system if you have access to all components. Because you have here the hardware inputs, the communication from the controller, which was basically added to the camera, and you have the changes in the FPGA code, which allows for the additional overlay, and you have some code which is running on the ARM cores and creates the game. And all this is basically what you want to do with a camera which is configurable and accessible and open.
Okay. And you can play Pong outside on the booth that we built up if somebody wants to try. We actually brought the Pong controllers with us. So, a little bit about the imaging pipeline inside the camera.
Yeah, here's an overview how we solved the actual camera problem. We decided to do 2 different pipelines in the FPGA. Basically one which starts at the sensor and ends by storing the acquired raw image, so no compression, no special modification in memory. And a second pipeline which takes an image, usually the one captured from the sensor, and modifies it accordingly so that it can be displayed on a monitor attached over HDMI. Now, one of the questions which always came up is why HDMI and why only full HD output? This was basically a compromise we had to take with the development board, because we do not have enough output channels to actually output the whole data. The FPGA would be fast enough, but there are not enough pins and available connections to the outside, so we had to use the existing infrastructure, which consists of an HDMI encoder from analog devices, and this chip was also very unfortunately connected to the FPGA, so that we were limited, or we are limited to certain modes we can actually output. But nevertheless, we managed. We have full HD and reasonably good frame rate with 60 frames per second. The sensor can do a lot more, but we have no way to store the data or output the data to a recording device other than the HDMI. For example, to give you an idea how much data we are talking about on a 4K sensor, if we take a snapshot in full 4K RAW, so just a single frame, usually you have 24 or 25 or 30 frames per second, just a single frame, and you transfer it over gigabit Ethernet as available on the board. You have between 5 and 7 seconds at least transfer time. So it takes about, in our case, because the gigabit Ethernet is not using the full bandwidth, it takes about 8 to 10 seconds to transfer a single snapshot from the camera over gigabit Ethernet. And if you now imagine running with 60 frames or 100 frames or more, then you get a huge amount of data which has to be transported and stored somewhere. And this is definitely one of the most interesting challenges in this project. The FPGA has no problem processing this amount of data and even more. This is not really the limitation, it's more how to get it to a storage device in some way.
Yeah,
Okay.
Actually, from the 60 frames we can output from HDMI, there's no recording device that can actually record it. We can only record 30 frames per second max, because there is no device that can do more, simply as that. And there aren't any devices currently that can do 4K either over HDMI. That's soon popping up, we guess, but yeah.
Well, I'm sure there is some device which can record this, but there's no device we can afford for our project to put it in the right perspective, because we are trying to keep it simple and cheap, because we also want the developers to give the developers a chance to recreate what we are doing at their lab or home or whatever.
Yes. So now we will actually show you some footage that we shot with the alpha prototype, but there's a short disclaimer of what this is and what it not is yet. When you normally shoot a film, you have to develop it, not in the software development sense, but in the sense of raw color processing. So it's a bit like shooting an analog film, but not processing it, but just looking at the frames. So what you see now is kind of in a very raw state from the color science. The daylight images have a bit of a greenish tint still. The tungsten situations have a bit of a reddish tint, and it's just because we didn't go to the colorist yet, because we have to first edit the footage and decide what we want to do. They then go to the colorist, and what I created here is just a quick selection of clips that we have shot so far. Nonetheless, the sharpness and the overall image impression you can already kind of experience in the way that it will also be in the end. Regie bitte Vollbild umschalten und Ton aktivieren. With a bit of luck, we have the image up here, and with even more luck, it will play back smoothly. Yes, we can.
So keep in mind, all of this was recorded with the prototype, which is standing outside in the room. So,
which is currently the only device in existence on this planet, so it can't be any other prototype anyway.
Correct.
Okay, now the next step from where we are right now to where we want to be a little bit later naturally, after the axiom alpha, we want to introduce the axiom beta, which is meant as a kind of developer kit, early adopters imaging platform to where we want to be one day, the concepts that you've seen earlier. And from the technical point of view, the beta will be similar to the alpha, just in a smaller package, in a more lightweight package, because we are not using the microset, which is like this size.
Oh, we are actually going to use the microset.
I mixed it up, not
beta.
the set board, but the microset, which is just 10 by 6 centimeters big. And that way it will be smaller, more lightweight. We will use different lens mounts at that point. We only have a Nikon F mount on the alpha, but we plan to also use a passive EF mount, Canon, so no lens control yet, and a passive 4/3 mount. We'll still use a large diameter 12 megapixel image sensor, not the one that we are using right now because it's rather expensive, but one that is just a little bit smaller and just costs half of the price. There will be different interface modules that we will design ourselves and not like on the set board, use the ones that are on board already and implement it in the pure way. That way we can do HDMI, maybe even dual HDMI, and also maybe SDI if it works properly. We will also have 2 micro SD cards in an extended module where you can store images like in a normal snapshot camera. And all these are plug-on boards to the microset, so you have like a sandwich stack of hardware that you can easily modify, and that way also just attach the microset board into that assembly.
Basically, what we did is we listened to the folks who came to us with questions regarding the axiom alpha, and we listened to what they want to do with it and what they plan to develop with a camera like this. And we tried to fit as many puzzle pieces together to provide a relatively sophisticated development system for camera enthusiasts, but also for other applications like the industrial range, where you want to process some data in some kind of industrial process, or astronomy. We have many astronomers which are interested in a camera where they can do direct processing on the board, where they can select what data they actually want to look at, or filter out, or process. And also, of course, a solution which is for still photography, as Sebastian said, where you can use it as normal camera with additional features, and naturally also for the camera, for the movie camera part, which is the original purpose of this design. So it will feature a lot of things like accelerometers and additional processing units, I/O, exchangeable modules, so that you can easily interface to different other standards or non-standards, or create your own even, so if you want to. And it will connect directly, it will directly attach to the microset, so it's a quite compact design, which doesn't use up nearly as much space as the alpha design with the set board does.
Yeah. And one of the most common questions we get all the time is, what does the actual axiom alpha prototype cost so far? And the one we have outside, which is the only one, costs around 2,500 euros material price, because the image sensor, which is the most expensive part in the assembly, costs already around 1,300 euros. And many people who saw this prototype asked, when can I get one from you? Can you build one for me? And we said, yes, we can, but it's all handcrafted, so it will be very expensive. And that's why we came up with the idea to create a new minimized version that we can actually build in larger quantities for a reasonable price in the end.
So I think if we had created like 20 Axiom Alpha versions or devices, then we would already have sold them for like 2,500 or 3,000 euros.
But that's just the material price.
That's just the material price, so there is no point in doing that. And we want to make it scale, and we also want to make sure that we can continue to develop on the Axiom project. So, which brings us to the upcoming crowdfunding.
Just a quick view first at what the beta could look like. I prepared a video of that as well. This is currently in the CAD modeling software. On the left, you see kind of the innards of the camera, where you have the green PCB stack that you can see later from the side a little bit better. Then you have a lens mount attached to that. This is kind of what we call the skeleton version, because you don't need an outer enclosure if you just want to use it in the lab or in an industrial application environment.
So that will definitely be the hacker version.
And then we also have an enclosure that seals off the entire thing on the right, with a slightly modified lens mount version. And the cooling fan on top, symbolized by the black box.
Yeah. Just stop it here.
Yes.
It's not 100% accurate how it will look, but it gives a good idea. Basically, the backside, which here features a very large module, is not that large. It's only going about 1/3 or a little less, and features the dual micro SD modules, which is optional, so you can remove it. You do not need to have it, but you can use it and attach it. And on the front side, can you turn to the front side?
Yes, I'll try.
Maybe stop here.
Like this?
Yeah, that's good. Yeah. On the front side, you see some space between the lens mount and the first PCB, which
this here, right?
Basically will hold the I/O modules. So we don't have the I/O modules in this design visible. There will be connectors right beside, on the left and on the right side of the lens mount, which actually connect the I/O modules over high-speed connectors to the sensor PCB, which is the first one in this view. This gives an idea how the design roughly will look like. This is not a real board layout. It's just actually it is a real board layout, but it's more thought as mock-up to get an idea how the modules will look like and how they will connect. Basically, we will have connectors on the top and interfaces on the right and the left side. This is seen from the front now. So the microset attaches through the two blue connectors on the top and the bottom, and is on the back side, so it's behind. And the I/O modules are the half-opened parts on the side, which basically go on top, right beside of the lens system on the lens mount. That's the basic design for the Axiom Beta, and as you see, it's quite small. It's about 10 by 5 centimeters in size, and everything fits in this space. So we will not be larger or higher than the microset, except for the cooling system, which will feature an optional fan on top of the camera, basically where you have fewer on a normal camera. So it will
maybe you
look
have
similar.
seen the huge fan that we have on the alpha prototype, and every time people see it, they ask, "Oh, you must be generating a lot of heat in there," but actually it's just to test out different cooling scenarios, and we don't actually need to turn it on at all. It just makes the image noise a little bit better.
Yes, also in initial testing we had about 50 to 60 degree on the sensor without any active or passive cooling, which is too high for good images, but rather low for what we expected to see without any cooling. And with the current cooling solution, which basically just moves air from the bottom over the sensor to the FPGA and out on the fan, we get roughly 3 to 4 degree over room temperature, whatever the room temperature may be.
On the image sensor.
On the image sensor, yes.
Okay, the next slide is about...
yeah, this one is the dual SD module, and again, this is, in my opinion, a good example how extensible the design is and should be in future versions as well. Because one of our members, our contributors, is very interested in using the Axiom camera for still photography, and he wanted to have some way to store a lot of data on micro SD cards. And for this purpose, we decided to simply add a module which features 2 micro SD ports and has some means of selecting which port is actually used for storing data. This is all basically controlled by a single PMOD interface. And as we already had a PCB for this, we decided to put on some other stuff like a fan controller and similar on it as well. So it's a good example of how to extend the planned beta in several ways.
Maybe I can talk a little bit more about Gabe's application, because he actually not only does still photography, but he likes to do medium format still photography. And as you probably know, medium format digital backs are hugely expensive. But the way he wants to do it is to use a smaller diameter image sensor like the one we are using, and add 2 motors to move the sensor around inside the medium format area. That way he cannot snap quick moving images of people running or something like that, of course, but he can get a far superior resolution than any digital back that can currently exist on the market, because he can move the image sensor on sub-pixel accuracy, and that way kind of generate a super resolution image with the required amount of time, of course.
So basically a scanning backend for a normal photo camera.
Yeah. Okay, now a more in-depth look at what the crowdfunding campaign that we mentioned already is gonna look like roughly. Since it's targeted at early adopters and developers at this point, our idea was to kind of give it to them for free, which means for material price only, for the price that we have to, kind of the pile of money we need to actually build the devices.
So at cost.
Yes. But if you want to qualify for that, you have to help us fund the actual development cost that we have to cover before we can go into manufacturing. So the idea is for everybody who gives us 350 euros, roughly in that price category, in the crowdfunding campaign, will soon after the beta is complete, maybe I can give a little bit about a little bit of background about the development time of the Axiom Alpha. We started with the development pretty much a year ago, in July, I think it was.
Last summer, in July.
And had a working hardware setup at around Christmas. Maybe you've seen the first raw still that we posted with the Christmas setting. in December. And so in roughly 6 months, we created the hardware of the alpha prototype. Now with the beta, it will be similar, in some ways more difficult, but in some ways easier, as we already have some of the hardware, and as we already know some of the things, the things we learned from the alpha. But on the other hand, we also have to account for larger manufacturing volume, so that will also take a bit of more time again. But I think half a year is a good roadmap that we can aim for after the crowdfunding campaign is complete and hopefully successful. That is our next target now. The preparations are almost finished. You have seen the demo footage that we recorded already, but we're still in the process of finishing the kind of crowdfunding story around it in a video that has somebody talking about the project like us, what we are telling you now, and explaining what we are doing and what we target for and what we want to do with the beta and everything. But that should happen soon, sooner than later.
Yeah, and specifically why we are doing it.
Yeah. Okay, that's it from the main program from now. Are there any questions? We still have around 15 minutes. Thank you.
Thank you very much.
Thanks. You guys say something about power and also maybe about the possibility of synchronizing multiple cameras together?
Yes, actually we haven't had it in the slides, but you can take a look outside. We first started by basically designing some kind of power supply we want to use based on a switching power supply input and design, which allows us to have a quite
wide range
of input voltages. So we can handle between 5 or 6 volt up to 41 volt input. And after the switching stage, we add the necessary LDOs, which give the power supply for the microset, which is attached to our board and our components as well. So we will be able to run it on normal power supplies and as well as battery of various kinds, which is quite interesting for the film area. And to the synchronization, I've been asked that maybe by you, I don't remember, several times, I think, during the last days. Yes, synchronization is not a big problem per se, because you can very precisely trigger the sensor and so basically control when you start an acquisition. And of course, as you have complete control over the hardware and the software, it's easy to add some kind of synchronization information. Maybe just a simple signal which gets sent from one axiom alpha or beta in this case to the other one, or between, if you want to do it more complicated, you can do it over time codes. You can send or generate a time code on the camera or sync up to a time code which comes from outside. We don't know what actual I/O interfaces we will design or provide, but in the worst case scenario, you just design your own I/O board, which is quite simple to do at this stage, or will be quite simple to do, and plug it on the camera, and you have your perfect synchronization to the next one. How much power? We currently have about a maximum of 2 watts per sensor for the sensor. And we, depending on what code you're running on the FPGA or what implementation you are running on the FPGA, it gets up to 5 watt on the FPGA side.
Yep. Maybe I can, about power, I'm just looking for the slide. In the assembly of the Axiom Alpha prototype, Regie, please, the slide, no, that's, no. There it is. You can see a huge battery pack here. And I don't know how many watt hours, I think it has around 50 or 60 watt hours. And on no project that we shot with this setup, we were able to drain even remotely the amount of power this battery pack provided into the camera, even for an entire day. We don't have exact monitoring options currently to see how much voltage or how much power we are drawing, but it never went anything near the problematic area. But for the beta, the power monitoring and the power requirement monitoring is much more sophisticated and already in the designs of the hardware.
The beta will have several sensors to monitor certain voltages and current used to generate power profiles, so where you can tell the FPGA is using so and so much power currently in this setup, and the sensor is using that amount of power, and so on and so forth. So that's basically to figure out how much is
you should consumed. Be pretty accurately be able to predict the amount of time you still have left on that battery by the voltage drop that you see.
And for this battery, this is actually a replacement battery for uninterruptible power supply. So a rather small battery.
Small but heavy. Good for shoulder shooting. Any other questions?
Yes, I've got two actually. One thing is, for many scientific and astronomical applications, it makes sense to cool the sensor down. So is that possible with the current hardware design? And the other question would be, how much experience, how much tools, and how much connections would, say, a larger hackerspace have to have in order to produce one of these cameras, perhaps the alpha design, completely by themselves?
Okay, to answer the cooling questions, we thought about adding some kind of Peltier element behind the sensor to do the cooling, which is quite a possibility, but we decided not to do this in the initial beta design. For several reasons. One of them being that the sensor manufacturers have already figured out that some kind of Peltier cooling or thermal transport is a good thing to do, and now start integrating the thing into their sensors. So there are already sensors available which have the Peltier element basically integrated in the package. And using such a sensor, as we will definitely support different sensors on the beta, which means different board layouts for it as well, we will start featuring such sensors, and they might be of special interest. But there's it's not such a big problem to cool it, actually. With most sensors, you definitely want some kind of socket, because you do not want to solder the sensor directly on the board. And if you have a socket, you usually have a space between the board and the sensor. And you can put some kind of metal sheet between the board and the sensor and use that for cooling. We haven't tried this yet, but we verified that it is feasible.
And about building a camera at the hackerspace, that's exactly what we did in the end at the local hackerspace. And the enclosure is laser cut. The PCBs are reflow soldered in the hacked reflow oven. And
no, actually, they were reflowed at home on my stove.
On the hacked stove.
Because I didn't even bother to use an oven for that. It was simpler to reflow solder the part which needs to be reflowed on a simple hot plate, basically. And the rest was hand soldered. So it's doable. You need to have some soldering skills, otherwise you end up smelling like chicken. And but it's doable, and everything is available online. We already had one person which successfully completed a recreation of the Axiom Alpha Interestingly, it's a person from China. So they invested some time to build the various parts and get them together. And we already received images from the device and the actually working sensor.
Yeah. So to summarize, it's not a big deal. You just have to kind of dedicate a certain amount of time to actually do it.
Okay, next question. Have you ever thought about the option of a two-lens stereo camera?
Yes, but the traditional stereo 3D setup for cinematography is that you use two actual dedicated cameras and a mirror rig to change the distance between the lens centers and the stereo base for that sense. Yeah, I can imagine.
But to answer this one, I thought about this several times already, because the question always appears, and usually it's answered by some mirror system or whatever. I think it can be done quite simple with Axiom in general, because there's no real reason not to turn the sensor like 90 degrees on the beta. And if you turn the sensor like 90 degrees and you put two devices side by side, you will have the perfect or even smaller spacing for the eye distance you require for a proper 3D setup. And of course, as the boards are side by side, you can easily connect them and synchronize them and control them in parallel. So I think it's not a big deal to do something like that.
And we have time for maybe one short question more, and just one comment. It's an open source project, so if you wanted stereo, then make one. So one more short question. Anyone have a question? Got 2 minutes. No? Well, thanks for that fascinating talk on this great project.
Thank you.